Hey everyone, my name is Bridi Valentim. I'm a PhD student at the University of Alabama, and today I'll be presenting our study, and it also belongs to my two advisors, Dr. Sriram, Aaleti, and Dr. Michael Kreger. The title of the study is The Correlation Between Test Methods to Characterize the Tensile Behavior of Ultra-High Performance Concrete, or UHPC. Okay, so here's our outline of this presentation. We'll start with the motivation why we're doing this study, the objectives, what we want to achieve, and then we're going to go through the procedures and the experimental testing and the results we obtained from the experimental testing, and we'll go through the summary and conclusions of this work. When it comes to the experimental testing, we're going to be analyzing three different test methods: the direct tension, 4-point bending, and geometry, or a test method that might not be very familiar to everybody, which is called double edge wedge splitting test. And from these test methods, we're going to draw basically three main sections of the results. The first one is a gauge length study, a comparison between the test methods, and a fiber distribution analysis of the specimens. So our motivation was basically the tensile strength of the UHPC, or ultra high performance concrete. Currently, we know that there are several existing test methods to evaluate the tensile strength of UHPC, and each test method has its own advantages and peculiarities. However, there is still a lack of agreement on which test is most suitable for analyzing and characterizing the tensile strength of UHPC. So on the bottom left is a graph that represents our stress strain behavior of the direct tension results. We start with an elastic response right here at the bottom left, and then we go through a strain hardening phase, and after the peak load, we go through a softening phase of the material. And on the right here is just a specimen representing what we have studied. I'm having some difficulties trying. Oh, there we go. So one of the objectives of this study was to basically come up with a tensile strength of the UHPC, or ultra high performance concrete. And first, we're going to take a look at the direct tension test method. And on the bottom left of the screen, we have an image that represents both the direct tension prisms and the 4-point bending specimens. We also have the deuce, and this is the shape of the specimen, how it looks like. It's a square with two triangular grooves and two notches. And after getting the tensile strength of the UHPC from these three test methods, we're also going to statistically correlate the test methods and see how they correlate with each other. We also are doing a gauge length study based on the results obtained from the direct tension prisms. We are obtaining a fiber distribution analysis from the direct tension and 4-point bending studies. And in the very end, we're going to do a UHPC material flow study from the direct tension specimens. Our UHPC used in this study was provided by Lafarge, and the name of the project is the Ductile JS1000. On the right of the screen, we can see our mix design, and we are using steel fibers that are 2% by volume. And at the center right here, we can see how this material flows. So talking about the formwork and how we prepared our formwork for this UHPC for our specimens, we basically use a computer numerical control machine for the deuce formwork, just because the geometry is sort of irregular and we didn't want any shape defects to affect on our results. Also, whenever there is a surface that is a contact between the UHPC and the wood, we made sure that to make that surface impermeable, just so the wood wouldn't soak the water out of the UHPC and interfere in our mix design. So we use a waterproof rubber coating on the sides or on the walls of the deuce specimens in an acrylic base. And a similar concept was used for the beam formworks, where we use a waterproof adhesive layer to prevent the contact of the UHPC to the wood. This was our mixer that we used in our pour day, a Mortarman shear horizontal mixer. And while we were pouring the UHPC, we also made sure to pour only from one side for all specimens. This way we'll have a free flow and a preferential orientation of the fibers in such a way that the crack of this specimen would be perpendicular as much as possible to the fibers. This was our test setup that we used for all of the specimens we tested. We have a MTS machine that was used in a displacement control, the specimen here in the middle. We had a time-lapse camera taking pictures at every 30 seconds or so that would help us understand better the behavior of the material under the testing. We also had an NDI opto-track system, which basically captures the movement of several LEDs placed on the specimens and captures the movement in the X, Y, and Z directions. And with that, we can obtain the displacement of the specimen, the deflection, and the strains. The first test method we're going to talk about is the direct tension test method, in which basically we pull the specimen or apply the tension force under a displacement control of 0.001 inches per second, and typically after testing we observed a single crack. The 4-point bending or third point loading test method was adapted from the ASTM C1609, and the loading points divide the span into thirds, and we applied a constant displacement control of 0.015 millimeters per second, and typically our specimens failed in between the two loading points. Now this is the deuce or a double edge wedge splitting test method, which it's composed of a square, as we can see here, two triangular grooves and two notches. We apply a vertical force, and this vertical force, when we have our friction equals 0, the resultant force is a horizontal force like this that would be equal to the vertical force, and this would give us a resultant tensile force, a tension force that we could, based on that, compare directly with the direct tension test method. So to ensure that the friction would be as close to 0 as possible, we applied grease in the interface between the grooves and the rollers, and we applied a displacement contract first of 0.002 millimeters per second until we obtain peak load, and after peak load up to 20% of the peak load or 80% of the drop of the force, we double the rate, and after that we double the rate again until the force observed was close to 0. So talking about our results, our first result was about the gauge length study. As we can see on the left side of the screen, we have 4 different gauge lengths based on combinations of pairs of LEDs, and as we see here, we have strain 1, 2, 3, and 4, and as the strain number increases, the initial gauge length also increases, starting from 1.5 inches and going up to 5.5 inches. What was observed in that is that the greater the initial gauge length is, the steeper the slope is in the strain softening region, as we can see here from strain 1 going down to strain 4. We also observed that for the same peak strength, for example, for our specimen DT7, which was 1.12 KSI, the strains would be different for the same peak strength based on the initial gauge length. And it's easier to see that better in this graph right here. As we can see, for the same peak strength for the same specimen, strain 4, for example, was less than half of what was observed in strain 1. So when we're talking about the comparison between the deuce and the direct tension test method, we're going to classify the failures of the deuce specimens into 2 types. The first one was observed to be about for half of the specimens, a single crack, a straight crack, and the cracks would start and end at the tip of the notches. And failure type 2 was exactly the opposite of that. We had multiple cracks. It didn't go through a straight path, and the crack typically didn't start or ended at the tips of the notches. And when we compared these two test results, we saw that the averages were 1.22 and 1.06, and we did run a statistical analysis, a two-sample t-test with a 95% confidence interval, and we saw that there is not a statistically significant difference between the two simple means. However, when we calculated and ran the same t-test for the specimens type 2, we saw that there is a statistically significant difference between the two simple means. Now, to obtain the direct tension results from the 4-point bending analysis, we had to do a 4-point bending inverse analysis to obtain the direct tension for these specimens. And so the way we did that, we know that we have our force applied on the specimens, and our specimen fails. And based on the load that we applied and based on a simple structural analysis, we can obtain the experimental moment. Also, as we can see here on these LEDs on the left side of the screen, based on the movement, we can obtain a strain, a horizontal strain, based on the horizontal movement of these LEDs. And from that strain, we can actually obtain the curvature of the specimens. And from this horizontal curvature, the horizontal strain, which we obtain the curvature and the experimental moment, we can obtain an experimental moment curvature curve. Aside from the experimental one, we also had a calculated moment curvature curve. So this was calculated based on a predefined stress strain curve and the specimen geometry. So we first predefined a stress strain curve for the tension and compression zones, and it's composed of 4 lines in the tension zone and 2 lines in the compression zone. With a linear strain assumption, we can see that the shape right here of the stress profile is similar to the tension zone right here, and it's the same is applicable for the compression zone. And how we did this was to an iterative process. It's a code that we created in Excel, that at first we assume just a random compression force, random tension force, and a neutral axis. And from that, we play around with shifting the neutral axis, and we can obtain the neutral axis, the height of the specimen, which was measured with a caliper, and the compression strain based on this stress strain profile here assumed. With that, we can obtain the tension strain at the very bottom of the specimen and the curvature of the specimen. After that, we can combine what we just found, the tension strain, with the predefined stress strain curve right here, and the compression strain with a compression zone profile. And then when we combine these two, we can obtain the stress profile, which is the resultant tension force, the resultant compression force, and the distance between the neutral axis and these forces. After we do that, we can finally obtain the calculated curvature and the calculated moment, which gives us a calculated moment curvature curve. So we just saw how to obtain the experimental and the calculated moment curvature curve. So what to do with that is easier to see here in this slide. We'll have an idea of the big picture, which we have some experimental results that we get, the horizontal strains and the applied force. With that, we can obtain the experimental moment curvature diagram. And then with that, we can obtain basically half of the inverse analysis. With what's highlighted in yellow, we can obtain the orange curve right here. And with the iterative process that we saw in the previous slides and the predefined stress strain curve, we can obtain the calculated moment curvature diagram. And from that, we basically obtain the blue curve right here. So the experimental curve, we know that it's something obtained from our experiment, so we cannot change that. What we can change is actually the predefined stress strain curve that we can play around with the numbers until we have a match. As soon as we have a match, we know that the predefined stress strain curve is the curve, this direct tension curve for the material that we obtained. After we did that and we obtained the tension curve for the 4-point bending specimens and the direct tension specimens, we did the same thing, t-test, comparing the averages and the standard deviation of each test method. And we saw that there is a statistically significant difference between the two simple means. And we were curious to understand why that was happening. And one of the conclusions we reached after we did our fiber distribution analysis is that as we go up in the analyzed cross-section of the specimen, we saw that the number of fibers was decreasing, which leads us to a higher calculated bending moment. And it's easy to see this in this image right here. We have a minimum amount of fibers at the top and the maximum amount of fibers at the bottom. With a higher amount of fibers at the bottom, there is a higher resistance to tension at the bottom, which leads us to a higher moment capacity and a higher numbers for the stress curve. We also compare the Dew's test method, or the double-edge wedged splitting test, with a 4-point bending analysis, and we saw that the results were in fact not statistically significant. There were not statistically significant difference between the means of these two specimens. And we did a fiber distribution analysis with the 4-point bending specimens and the direct tension specimens, in which we analyzed each row and each column of these specimens. And we, for simplification purposes, for example, for the 4-point bending specimens, we divided the cross-section into 4 areas: area 4, area 3 and 4, and area total. Please have in mind that this area is not actually the area of the cross-section, it's actually the areas of all the fibers that are in each area. So for example, if this specimen is 3 by 3, it's not going, area T is not 9 square inches, it's actually the area of all the fibers that are seen in this cross-section. So talking about the fiber distribution in the 4-point bending specimens, when we look at the stress strain profile, we see that we have 5 points here basically, and there is a big table here on the right hand side. However, I want us to take a look at the bottom line right here. Let me explain this table real quick. On the left side, we have the average values, the standard deviation, and the coefficient of variation of each individual point right here, as we can see on the graph on the left side of the screen. And up here we have this, the first column is the actual stress that we observed. And these 3 columns here represent the stress divided by the area of the fibers in each respective area, area T, 3 and 4, and 4. And this row right here, the error, is basically the difference between the numbers we found in these 3 columns, how different they are from the actual number from the stress. And with that, we found that the stress over area 4 resulted in the lowest average error. So we concluded that the area 4 has more influence in the stress of the specimen than any other selected area. And we did something similar for the direct tension specimens, in which we analyzed the area fibers in the entire cross-section and the rows 1, 2, 3, 4, and all the columns. And we did something very similar. Attention to the bottom of the screen right here. This is the row we're looking for. And we saw that when differently from the 4-point bending specimens, when we analyze the entire cross-section, it actually has more influence in the specimens than all the other selected areas. So after we saw that, we did a study on the stress versus the number of fibers, and each data point here represents 1 specimen. And we saw that from this regression line, we saw that the UHPC played a role of 72% on the peak stress, and the fibers played a role of 28%. keep going with the fiber distribution analysis. Now we're going to talk about the flow analysis, in which we cut the specimens into 5 different locations and analyze the number of fibers in each cut. And we saw that there are less fibers at the end of the specimens than in the center. And to understand better how this looks like, we plotted a 3D graph of the number of specimens down here and the cuts. And the z-axis is the total number of fibers. And we can see that at places where we have a peak number of fibers, there is actually, where we have the peak is at the center of the specimens, and this point right here where we have a very low number of fibers is at the end of a specimen. Okay, so this graph right here represents the rows in the specimens. As you guys remember, row 4 is at the very bottom of the specimen cross-section and row 1 is at the very top, and we can see that there are less fibers at row 1 than at row 4. So as we have talked about that before, as we go up into the analyzed cross-section, the number of fibers actually decrease. Going through the summary and conclusions of our studies, we saw that the gauge length, with a higher initial gauge length, we actually have a steeper slope in the strain softening region. We have a smaller strain at the peak stress. Comparing the direct tension specimens and the double edge wedge splitting test specimens, when we get type 1 and 2 and compare with the direct tension specimens, for type 1, there is not a statistically significant difference between the two samples when we use a t-test with 95% confidence interval, and the opposite is shown to be true for type 2. When we compare the direct tension specimens with a 4-point banding, we saw that there is a significant difference. And this is probably because, as we talked about that, as we go up in the cross-section, there are less number of fibers and a higher calculated bending moment. And when we compare the 4-point banding and the Dew's test methods, we saw that there is not a statistically significant difference between the two simple means. And when we did the study of the fiber distribution on the direct tension specimens, we saw that the UHPC played a role of 72% of the peak stress of the direct tension, and fibers played a role of 28%. We also saw that there is a less fiber percentage, a lower fiber percentage at the ends of the beams, and that there is a higher fiber percentage at the bottom of the beam cross-section compared to the top. I want to thank you guys for watching for this presentation, and I would be taking any questions you guys might have now.
Thank you, Daniel. Very nice talk. Let's see if we have any questions. So the first question is, what prompted the Dew's test setup with the double edge wedges? Is that common for UHPC testing, and is that a standardized ASTM method?
Jova, I'm sorry, I couldn't hear you. Could you please repeat it again?
Yeah, sure. So what prompted the use of the EWS, I believe you pronounce it Dew's, test setup with the double edge wedges? Is that common for UHPC testing? And is that test method standardized with ASTM?
Oh, perfect. Yes. So the Dew's, I believe there is not a standardized test method about that. We obtained this idea by a study in Italy in which they used the same specimen geometry for fiber reinforced concrete. I have never seen a study with this geometry for UHPC. I believe, as far as I know, as far as I have researched, this is the first time somebody has used this geometry on UHPC. And as we saw that that specific study from Di Prisco in Italy obtained a good result when compared to a direct tension test method, we thought it would be interesting to try to apply the same thing and see what we obtained for UHPC.
Okay, thank you. The next question is, why didn't you use the splitting tensile test? Was it not suitable for UHPC, or was it a matter of scope?
The splitting tensile test, we did use some other test methods, but for this specific topic, for this specific study, we only use these three. But in our research, we're doing other types of test methods as well. We just haven't published yet the other test methods.
Okay, great. We have a comment also, for UHPC to be more widely used, commercial labs need to learn these tests. What would you recommend, I guess, as far as the adoption of these test methods is concerned?
So for UHPC to be widely used, it's true that some test methods have to be standardized. And one of the main reasons we're actually pushing or studying the DUSE test method, it's because you need a compression machine. For example, for the direct tension test method, you need a machine that's able to perform tension tests, and these machines are usually more expensive. So with the DUSE test method, if we can prove that this is a very reliable test, the labs will only be needing a compression machine to obtain the tensile strength of the UHPC, which would be cheaper and I believe more accessible for labs.
Okay, and the last question is, what influence would size effects play? Does the speaker expect similar tensile strength results in larger test specimens?
That's a good question. We haven't studied the size effect yet, to be honest, because it's a very valuable question because, of course, when we change the size of the specimens, the size of the fibers, for example, are not changed. So our fibers are 13 millimeters long, and for smaller specimens, what a crack that is going to go through a fiber in a specific direction might be similar or might have a different result from when we have a larger specimen. So the scope of the study was only in between the different test methods, but I think it's very valid to have a study including the size effects as well and see how that plays into different sizes of different specimens.